Hey all, I wanted to make a little video about supporting multiple hardware configurations for your embedded Rust project. Because say you've got a very nice project. Take this one. This project is awesome. Firstly, because it's in Rust, of course. But also, I've been hard at work at making a really cool feature because this chip on the STM32L4, it boots up, configures a UART, and then has a UART echo server on it. It's really amazing. So amazing, I'm going to show you. Look at that. Compiling, flashing, and now this board, I've got it right here. This board is now an echo server. And it even printed out, hello embassy world. It's really amazing how I typed this and didn't take this from the embassy examples at all. Anyway, we can print stuff to it and it'll print it right back at us. Really cool. So our boss is very happy about our project because it does exactly what it needs to do. But then our boss apparently went to Embedded World and he visited the STM booth and he saw that a new chip was released by STM, the U0. And apparently our boss really likes that chip and he wants to switch to it because apparently like the people at STM, like they gave him a dev board. I mean, it's nice they do it, but now our boss wants to change to it. Oh man. So we ask like, okay, we can change to it. But then your boss or our boss says, no, we need to support both. Because it turns out our boss, just before he went to Embedded World, he ordered 10,000 pieces of the L4 chip. Yeah, we're not getting rid of the L4 that fast. We really need to be able to support both. So how do we do that? There are multiple ways to do it. For example, we could create a board support package, which could look roughly like this. Say our board had a microphone, but now our microphone for some reason had to be on different GPIO pins. We could make these configs that would select the type of pin and use type aliases for that. So in all our functions, we can then use the correct type. This is fine to do, I think. People have made great software using this. And actually, Embassy does it as well internally. For example, here's a function from the ADC module from Embassy. And here we can see that Embassy has added support for all kinds of STM chips. And STM has been busy at adding new features to their chips. For example, a 16-bit resolution to their ADCs. We see Embassy using some configs here to be able to support it when a chip is selected that uses the fourth version of the ADC. And when you do this in a limited way, like here, maybe like here, this can work out pretty well. But keeping up with this, I think, is not very great. For example, maybe you've got a very old board that you don't really use anymore. Who's really testing it if everything is actually going all right? So really, if you're going to do this, you need to have a good CI setup. And I know not everyone has that. So there's another way of doing this, and I'm going to show you on in this project again, because we want our echo server on the U0 as well. So let's first try out the U0 and see what's different. So I've built it here already. And we can see the project looks very alike because, well, we're using the same hardware abstraction layer, namely Embassy. But there are different things. For example, the interrupt is now called something else. We have different values for our clock setup because this chip is not 80 megahertz but 56. And the pins we're using are different. But in this case, we could do it all with like config statements and selecting everything at compile time. But say our change was even bigger. Maybe our boss wanted to move to like a Nordic chip and NRF52 maybe. Then the interface of the HAL would actually change a lot, and then using configs would be extra bothersome. So a different way to do this is to use the abstractions that Rust actually gives us, namely traits and generics. Because in this case, our echo server really just takes a stream of data and outputs a stream of data, which is something we can relatively easily define traits for. Even better is that we don't have to define a trait at all because it's already done for us, namely from this crate embedded IO, which replaces the stud IO. Because on embedded we don't use the standard library, so we have to miss these traits. Most important here are the read trait and the write trait. And what Embassy does is it already implements those traits on our UARTs. So what we can do is we can refactor our application code to a different library, which I've done here already. We see the same code here, and that's really because secretly I was already using these traits. But what's most important here is we've got this function here. We define a generic UART. We take the UART as a parameter, and we specify that the UART has to implement the read and the write trait. Then we put our implementation here. And now we can actually refactor our U0 and L4 code to use the shared library. So here in the L4, we can remove this, and we can call the UART echo function, and pass it our UART. And now we can rerun it again, and it'll print it out again, and everything still works. We can do the same thing on the U0. So if I replug it like that, I can show you that the U0 works as is. It's actually on the COM4 this time. Let's clear the data, let's reset it, and it prints out. But now instead of like duplicating the logic, we can call the UART echo function here as well. And it'll still work. It'll print it out again, and it'll still echo. And now the really nice thing is when we change the behavior of this. So say hello YouTube. If now recompile, it'll say hello YouTube. And without any more refactorings, if I recompile the L4 chip, which I need to replug again, now automatically this will have the new version as well. And reset, yes, and everything works. So I think this is a really great way to do it for embedded Rust. And this actually, if you think about it, is also the same way that we write device drivers for Rust. Now there are some things where this is less great for. For example, when you have a really specific hardware feature you need to use that's difficult to encode in a trait. Because we don't have to reuse traits, we can write our own traits as well. So there are always like a tons of way to do anything. But this is something that you've got in your tool belt as a Rust developer as well. That was really all I wanted to say about this. If you need some help getting started with Rust or are running into some problems when you're already using Rust, make sure to check us out. I'm the embedded tech lead at Tweede Golf, and we're a consulting company where we do lots of Rust engineering, both embedded and system software, and a little bit of web as well. We give trainings and workshops, so for anything Rust related, you can contact us. Visiting our website is also really useful just for visiting the blog. We've got lots of stuff here, both high level and low level, systems and embedded. And one I wanted to show you is this one, building an async runtime in Rust, where my colleagues dive into the nitty-gritty of async Rust and how it works under the hood. Really interesting. This is specifically for desktops, but it's also very applicable to embedded. Embassy looks a lot like this as well. So that's all I had to say. Thanks for watching the video, and maybe until next time. Bye bye.